In this video, we're going to look at giant ionic structures. And so giant ionic structures have what we call ionic bonding. And again, just like with metallic, if we're asked to describe why a property of an ionic compound is the way it is, we won't just be saying because it has ionic bonding. We'll be talking about the attraction between oppositely charged ions. So ionic bonding occurs when we have a metal bonded to a non-metal. So for example, sodium chloride, potassium nitrate, magnesium oxide. Electrons in these are transferred from a metal, so metals lose their outer shell electrons to become positively charged ions, to a non-metal. Non-metals gain electrons to get a full shell and become negatively charged ions. So metals lose to become positively charged. Na becomes Na+, Mg becomes Mg2+. Non-metals gain to become negatively charged. Chlorine becomes a chloride ion by gaining 1 electron. Oxygen becomes an oxide ion by gaining 2. So we're going to show outer shell only electrons. So we're not going to bother with the inner shells. We're going to show the outer shell electrons. So if we take a sodium atom, sodium's electron configuration, it's got, if we look on the periodic table, it's number 11. So 11 protons, and the atom would therefore have 11 electrons. 1s2, so 2 in the first shell. 2s2, 2p6, that makes 8 in the second shell. 2 in the S subshell, 6 in the P subshell, and then 3s1. So in the outer shell, if we were to draw the outer shell onto our sodium atom, it would have 1 electron on the outer shell. If it then loses that electron to become an Na+ ion, that has got the electron configuration 1s2, 2s2, 2p6, it loses that 3s electron. And so there are no electrons in the outer shell now. We put it in a bracket and show that there's a charge of a 1+ on the sodium ion. And then if we were to look at a chlorine atom, so if you look in the periodic table, chlorine is element number 17. So 1s2, 2 in the first shell, and in total 8 in the second shell. 3s2, that's the first 2 in the third shell, 3p5, that makes 17 altogether, 7 in the third shell, 7 in the outer shell, that's why it's in group 7. So if we were to draw chlorine with its outer shell, then that outer shell has 7 electrons on it. 2 in the S and 5 in the P. So we can see that we've got an unpaired electron on chlorine. The chloride ion would become Cl- by gaining 1 electron to fill the third shell. And so that chloride ion, if we draw our shell on, we do need to draw the shell this time because we filled a shell, would have the 7 that it had before, and then it's gained 1, and in this case we're talking about from sodium in sodium chloride. So we've got 7 crosses and 1 dot. As long as you have a different type of electrons, called a dot and cross diagram. I've used dots for sodium and crosses for chlorine. You could do it the other way around. You end up with a 1- charge because you've got 1 electron that didn't belong to chlorine originally. So what would that look like when those arrange themselves in a giant ionic lattice? So the lattice in sodium chloride, remember that giant means endlessly repeating, and lattice means a regular pattern of the oppositely charged ions. So we're going to go positive ion, negative ion, positive ion, negative ion. Now if we look at the electron configurations, we can see that the negative ion has got more shells than the positive ion, so it will be bigger. So we're going to go sodium, and then a slightly bigger chloride ion, and then back to a sodium. Now if you drew these the same size, you would still get the marks bigger chloride, smaller sodium, bigger chloride. And can you see how I'm alternating between the smaller sodiums? So every smaller sodium is surrounded on all sides, left, right, up and down, by a chloride ion. It would also be in front and behind, so each one would be surrounded by 6. So the sodium ions here, the smaller positive ones, and the chlorides are 1 minus. So this is my Na plus ion, and this is my Cl minus ion. Now this is a 3-dimensional lattice. In reality, this is a 2-dimensional cut-through diagram. But if I was to imagine the 3-dimensional lattice, so thinking that a sodium is next to a chloride, and if you imagine, they're not actually bonded with a covalent bond, so just be careful. I'm just drawing a dotted line to show how they're arranged in a what we would call a cubic lattice. So every Na is next to a Cl, every Cl is next to an Na. So we're alternating in a cubic pattern, Na plus and Cl minus. So we've got this cubic arrangement. So every sodium is surrounded by 6 chlorides, every chloride is surrounded by 6 sodiums. And that is a giant ionic lattice, oppositely charged ions, whereas a giant metallic was positive ions with negative delocalized electrons. So what does that mean for formulae of ionic compounds? Well, since if we're in group 1, we have 1 outer shell electron, 2 for group 2, 3 for group 3, 5, 6, 7, etc. Then if we're in group 1, we would lose 1 electron. If we're in group 2, we would lose 2. If we're in group 3, we would lose 3. Because groups 1, 2 and 3 would represent where we would find the metals in the periodic table, whereas groups 5, 6 and 7 would be non-metals. So group 5 would gain 3 to get to 8. Group 6 would gain 2 to get to 8, and group 7 would gain 1 to get to 8. And so we form a 1 plus ion with group 1, a 2 plus with group 2, 3 plus with group 3, 3 minus with group 6, 2 minus, and just minus like a chloride ion. So borons in group 3, it doesn't usually form ions, it usually forms covalent compounds because it is a non-metal in group 3. Group 4, they usually form covalent compounds, but tin, you might see SN4 plus, and lead, you might see 2 plus and 4 plus. Transition metals have a variety of stable ions, like e.g. we could get Fe2 plus and Fe3 plus. So let's have a look at dot and cross diagrams showing outer shell electrons only. So if we were to look at magnesium and fluorine, so magnesium is in group 2, fluorine is in group 7. So we know that magnesium will form an Mg2 plus ion, so it's going to lose its 2 outer shell electrons and have none, so become 2 plus. And a fluoride ion, it's in group 7. I'm not going to draw the circles because they do take time and they're not necessary. So fluorine's got 7 outer shell electrons of its own. It makes up the 8th with 1 from the metal, and so it becomes a 1 minus ion. Now, we've got magnesium that's 2 plus. Fluoride's only 1 minus, so we are going to need 2 of this F minus ion to balance the 2 plus charge, which means that the formula of magnesium fluoride is MgF2. We need 2 of them. Call it magnesium. Magnesium ion is just called a magnesium ion, but when fluorine becomes an ion, it becomes fluoride. Negative ions become ides. So let's do the same with sodium. Sodium's in group 1, oxygen's in group 6. So sodium loses 1 to become 1 plus. Oxygen is in group 6, 1, 2, 3, 4, 5, 6, and it gains 2 to become 2 minus. So in order to balance that, we're going to need 2 of the sodiums to balance the 2 minus charge. So we're going to have a formula Na2O. Sodium ions are called sodium ions, but oxygen ions are called oxide ions. We don't say oxygen ions, we say oxide ions. So aluminium is in group 3. So we're going to go Al, put it in a bracket and write 3 plus. It loses 3 outer shell electrons. Oxygen's in group 6, so just like above, the oxide ion is still the same, despite being in a different compound. 6 crosses belonging to oxygen, 2 dots coming from the aluminium, 2 minus. To balance these 2 charges, you would need to have 2 3 pluses, gives me 6 plus, and 3 2 minuses gives me 6 minus. So Al2O3. Aluminium oxide, IDE. So magnesium, group 2, nitrogen, group 5. So magnesium, group 2, 2 plus, nitrogen, group 5, 1, 2, 3, 4, 5. So we need to add 3 extra electrons to make it 3 minus. And so we get Mg. Right, so to make these both have the same charge, we'd need 3 magnesiums and 2 nitrides. Magnesium, nitride. Now, as well as ions that are elemental ions, ions coming from elements in the periodic table, we also have some compound ions, ions that are made of more than one atom covalently bonded together, but then ionic themselves. So they're carrying a charge, so they'll then make ionic attractions to an oppositely charged ion. So within the ion, we have covalent bonds, shared pairs of electrons, but we're then making ionic bonds to oppositely charged ions. So we have to learn these. This is a learning exercise. You need to know them. You need to be familiar with them. You need to be able to recall them straight from memory without thinking. We've got the ammonium ion, NH4+. That is formed when ammonia, NH3, reacts with acids to become the ammonium ion, NH4+. We've got the hydroxide ion, OH-. We've then got 2 types of nitrate. The one that you're more probably familiar with, nitrate 5, is an NO3- ion. Now if I were just to come up here and look at that, the 5 refers to what we call the oxidation state of the nitrogen, and all nitrates have a 1- charge because they come from the nitric acids, which have the formula HNO something. Now the 5 means how many oxygens would we need to get from +5 to -1. If you see that each oxygen is worth a -2, oxygen has a charge, oxide ions are -2, they use 2 electrons in their bonding. So -2, -2, -2, there would be 3 of those. Now the nitrate 3, if I was to change this to a 3, how many oxygens would I need to get from +3 to -1? You'd notice I only need 2. So this is NO2-. Cyanide is a CN-. That is a C with a triple bond to a nitrogen. Nitrogen has a lone pair, but carbon had 4 electrons. It's used 1 in each of these bonds. And then in order to make a full shell, that's 3 bonds is 3 pairs, which is 6 electrons. It's got 1 more, it needs to get 1 from somewhere else, and this is what gives it the minus charge. We will come back to the cyanide ion when we study covalent bonding, and you will see the structure more clearly. Hydrogen carbonate is the HCO3- ion, and hydrogen sulfate is the HSO4- 1 minus iron. Carbonate is a CO3 2 minus iron. Sulfate 4, a bit like the nitrates, sulfates are always -2. If this sulfur is +4, how many oxygens would make you go from 4 to -2? Well, we need to subtract 6, which is 3 lots of 2. So sulfate 4 is SO3 2 minus, whereas sulfate 6 is the one you're more familiar with, SO4 2 minus. So technically we should have put a little 6 after this, hydrogen sulfate 6. Phosphate, PO4 3 minus, and we can look at the charges on that and see that that does make sense. Because if the 5 is for the phosphorus, take away 8 is -3. So hydrogen phosphate is HPO4 2 minus. So we got, like I said, we need to go away, we need to learn those so that they just come out whenever we need them. What we're going to do now is use them. So how would we come up with a formula from a name? So we see this name, sodium hydroxide. What you want to say to yourself is, what is it made of? It's always 2 parts, 2 ions, a positive ion and a negative ion. So we've got the sodium ion and the hydroxide ion. So what's the hydroxide ion and what's the sodium ion? So the hydroxide ion we just need to know is OH minus. The sodium ion, sodium is group 1 of the periodic table, so it's a 1+. Now if those are the 2 ions, they balance each other nicely, so we get NaOH. So same again, what is the calcium ion? And then what is the carbonate ion? So only ever 2 parts. So calcium is in group 2, so 2+. Carbonate, we're just memorising, CO3 2 minus. So again, that balances, CaCO3. So we got the hydroxide ion and the barium ion. Barium, group 2. Hydroxide, memorised, OH minus. Barium needs 2 hydroxides to balance the 2+ charge. And because the hydroxide ion is a compound ion, we use brackets so that we can see that it's not just 2 H's, it's 2 of the whole hydroxide ion. So calcium nitrate. Calcium is in group 2, so it's a 2+ ion. Nitrate 5, we just memorise, is NO3 minus. So in order to put these together, we'd need 2 nitrates for a calcium. Okay, the next one, chloride, and we've got ammonium. So ammonium is a compound ion that we need to memorise, NH4+. Chloride is from chlorine. Chlorine's in group 7, so it's 1 minus. 1+ and 1 minus, so no brackets needed, no doubling up needed, it's just the 2 formulas put together. So what would this one be? Our negative ion is this part, and our positive ion is the sodium. So we would have sodium, and if we can think about our ions as well here, and then we would have the positive ion. Sorry, the negative ion. So sodium was the positive ion, that was Na+. The negative ion must be HCO3 minus, because there's only 1 of all of that for the sodium, and that's called hydrogen carbonate if we look up at the table above, or again, we're supposed to be memorising. So again, let's do this, sulfate 6 and potassium. Potassium's in group 1, 1+. Sulfate 6, we're memorising, SO4 2 minus. Put those 2 together because there's only 1+, we need 2 of them. Ammonium, hydroxide. Ammonium, NH4+, memorised. Hydroxide, OH minus, memorised. NH4OH. Let's look at the next one. We've got this PO4 as our negative and Na as our positive. So Na is an Na+ ion, that's called sodium. Since there are 3 NAs, then this PO4 must be 3 minus if there are 3 Na pluses. That's the phosphate, and that is the phosphate 5 ion. We've got to do the sulfate 4 with the ammonium here. So ammonium we've memorised, NH4 plus. Sulfate 4 is where we're SO3 2 minus. So we're going NH4 twice SO3. And then our last one that we've been asked to do is magnesium and phosphate 5. So magnesium is in group 2, using the periodic table. Phosphate 5 is PO4 3 minus. So we're going Mg 3 times, bracket, PO4 2 times. So what are the properties then of these ionic lattices? So whenever, again, like with the metallic, if we get a question about structure and bonding of ionic lattices, we need to first of all say that the structure is a giant ionic lattice and that the bonding is ionic, which is the attraction between oppositely charged ions. So negative and positive ions alternate. We drew this structure a little bit ago. And the giant ionic lattice is held together by, these are very strong forces of attraction between oppositely charged ions. As a result of these being strong forces, they're going to have high melting points because it takes a lot of energy to overcome the strong forces of attraction. Like as I said, you must always give the definition in order to score the marks between the oppositely charged ions. Strong forces of attraction between the oppositely charged ions. So do they conduct? Well, when they're solid, ionic lattices do not conduct. So ionic solids do not conduct. Why? Because the ions are fixed in position. They cannot move and carry current. But when we dissolve our ionic substances in water or we melt them, the ionic substances can conduct as the ions, and we must be careful that we don't slip into saying electrons, the ions are free to move and carry current. Ionic things are brittle. Where metallic things are malleable, ionic things will shatter if we hit them with a force, and that is because when we hit them with a force, we move one layer of ions over the next, and instead of being oppositely charged, the like charges line up, and then they repel and the structure shatters.